Hello there. I'm glad to see you all here enjoying PyData. Did you go to the opening talk?
Yes.
Yeah, brilliant stuff being done with Python in the notebook now. There were a couple of talks in PyCon Italy on the same topic. And I think it was very significant that Python, the thing that I thought was really most interesting was when he said that Python is now cool and that you recruit people by letting them use Python. I thought that the fact that opinion of Python has made it into the scientific world is brilliant. So, just before we start, a quick introduction. I've been programming for a very long time, since 1960 mumble, and I started using Python about 20 years ago in the mid-1990s. I have actually taught Python classes for a bit, and for 20 years I spent in the States principally consulting. I started a conference called PyCon in the USA, which is still going to this day, and I've tried to invest some time in increasing Python's popularity by being a director and chairing the Python Software Foundation. So I am actually a Python nutcase, and I'm currently employed as Chief Technology Officer for a fintech startup called BMLL Technologies in London here. I moved back from the States, in fact, 1 year ago today. So, everything that is in this talk is available, and I think if we can flip across, oh, that's very interesting. Yeah, okay, so there's what happened there? There's a GitHub repository. Where's my cursor gone? And so what we have in that GitHub repository, if I can bring it up, there we go. So besides the usual README, I've got the slides, which are available not only in the original PowerPoint form, but also as PDFs, because fewer and fewer people now are using PowerPoint. And there is an IPython notebook that I can use to actually show you the code executing, make sure that you know that I'm not trying to pull the wool over your eyes. And that's actually available in two forms. There's the one I'm going to be using in the presentation, which is pretty much just the code with a few headings. And then there's an annotated version which kind of expands on the material so that you can read it as you execute the code. So it's still got all the code in. And just in case there's anyone in the room who hasn't installed Jupyter yet, I have included an HTML version of the notebook file so that you can just view it without worrying too much about having to install any software. So that's the annotated version of the notebook, but what I'm going to be trying to do is, as I go through, I'll actually be using that notebook to help me demonstrate executable code. Very happy to have questions as we go through the talk. There is, as you know, probably a short question and answer session. Unfortunately, I can't stay for the rest of the day, so if you do have any questions that you want to ask me afterwards, please buttonhole me straight after the talk, because I can't stay long. My partner retired last week, and we've got 20 people coming to a party, and I've got to cook for them. So, unfortunately, I won't be able to stay for the rest of the day. So, a quick word about iteration. Basically, what you're trying to do when you iterate over something in Python is say, take the same action with every one of a number of objects. And so typically what we're really talking about is use of the for keyword. And the traditional use of the for keyword is in the for statement. But if you know enough Python, then you've also come across comprehensions like list and dictionary comprehensions. And so all of those uses of the for keyword involve Python's iteration mechanism. So just in case you're worried or concerned about it or wondering about it, this material doesn't apply to while loops, which use an entirely different mechanism and much simpler mechanism for looping. So Python originally used to do for loops back in the days before you could iterate over dictionaries, and back in the day when life was simpler, effectively by simply using the get item method. So what it would do is this is pseudocode. I mean, this is not what you actually had to do. This is what the interpreter did when you wrote, for I in test list. Then it would set some private index variable to 0, and then it would loop, and it would try to access the next value in the item, and it would do that by using the dunder get item method, which, if you're not familiar with it, is the method that's called when you subscript something. So basically what it's trying to do is it's trying to access successive values in the list. So if we have a list called test list, then it will issue get item 0, and then it will do the loop body with the get item with item 0. It'll increment the value, it'll go around, and eventually you'll get to the end of the list, and so the get item will raise an index error. The interpreter will break out of the loop, and that is the end of your for loop, with a few minor details, like, if the for loop actually broke with a break, then you don't do the else, various things like that. But that's the essence of how Python used to do indexing. And in fact, we can see in the IPython notebook, I've defined a few values here, so we're just there defining a simple function to represent doing something with things, and a sample list. So here is that actual code, and you can see that if I execute that code, it does indeed iterate over the list. So you all know Python's very good at backwards compatibility, and even to this day backwards compatibility is available. So we can actually write an iterable, if we want, of our own that uses that mechanism. So here I'm defining a stars class, and the idea behind the stars class is that the instances are initialized with an integer value, and basically it will produce a sequence of values increasing. So get item in this case it uses the index value to determine the number of stars that it returns. So if I execute that declaration and then I create an instance of stars 4 and I iterate over it, what will happen will be, I'll just have to scroll that up a little bit. So you can see that the get item method is called with an index value of 0 first, so the value returns the star, an empty string. Then get item is called with 1, so it returns a string with 1 star, and so on and so forth, until eventually get item is called with an index value of 5. And of course, with an index value of 5, it raises index error, and so the loop stops. So that mechanism's been available since about Python 1.5, something like that. It's certainly a very old mechanism, but around about the 2.2 stage, okay, we've just discussed all that. Around about the 2.2 stage, they decided that they didn't like that mechanism for a number of reasons. I mean, it has got limitations, like you have to have a get item method which takes a numerical value, and those indices must actually run from 0 up through a maximum value. So the real problem there is that you can only use that protocol to iterate over ordered containers. So it didn't work with dicts, it didn't work with sets. Anything that wasn't numerically accessible by index wasn't iterable in Python. And so the developers, being anxious to make the language as good as they could, introduced a new mechanism, and they said, okay, when we try and iterate over something, the for loop looks to see whether the object that we're iterating over has a dunder iter method. Dunder iter, by the way, is the way I pronounce underscore underscore iter underscore underscore. It's just an abbreviation, a syntactic abbreviation. So if the object that you're iterating over has a dunder-iter method, then the interpreter will actually call that method and save the result of it, and then as it goes round the loop, it produces the next value for the iteration by calling this object, this newly created object's dunderNext method. And if you're using Python 2, there's a little glitch in the design there because they originally called the method next with no dunders, but then they realized as they moved, well, in fact, they realized very quickly afterwards that it had been a mistake. But in Python 3, it's properly recognized as a magic method. So if that call to the next method raises a stop iteration exception, then the loop terminates. So that's what we do in the new protocol if there's a dunder method on the object. If there is no dunder-iter method, then basically it just falls back to the original getItem based mechanism that we were discussing. And as I've already demonstrated, that mechanism works perfectly well, even in Python 3. I think I'm running Python 3.4 on this particular demonstration. So these new types of objects, those are called iterables. An iterable has a dunder-iter method, but it will not have a dunderNext method, because remember the for loop uses the result of calling dunder-iter to call the next method on that. It doesn't call the next method on the iterable object itself. So if you look at lists and tuples and dicts and sets and many other types of objects in Python, in fact, some of them that we don't normally create ourselves but are created by mechanisms within the language. In short, basically anything you might want to iterate over, Python has provided the iteration mechanism for, and so they are iterables. So the pseudocode for the new iteration protocol, here we're trying to iterate over test list again. So in this case we call test lists iter method, and then we store that in a private variable. I've just used the single underscore as the variable name, and then we go through we operate an infinite loop, and we call the dunderNext method of this object in order to retrieve the next item in the iteration. If calling that method raises the stop iteration error, then that's the end of the iteration. Otherwise, we do something with I. And there's an example in the notebook here. So you can see, by the way, that you can't iterate over everything. So if you try and iterate over none, it will say type error, non-type. I beg your pardon?
Can you make the text a bit bigger?
Can I make the text a bit bigger? I would imagine I can, yes. How's that?
A lot better.
Thank you very much. Yeah. So basically what's happened there is that the interpreters looked at the non-object and it said it doesn't have a dunder-iter method, it doesn't have a dunderGetItem method, I've got no way to iterate over this thing. So if we take a look at the listing of all I've done there is I've taken a list of the methods and variables accessible from the non-object, and you can see that neither iter nor getItem is in there. I suppose another way to do it would have been to say present the result of has iter none dunderiter. Same thing, it just says there is no dunderiter method, there is no dunderGetItem method. So if we actually write the pseudocode for the list with my test list, you can see that it does actually work perfectly, and the reason that it uses the new iteration method is because the test list does indeed have a dunderiter method. So if we call that dunderiter method, what do we get back? Well, the answer is that this is a special type of object, so calling dunderiter, which is what I've done here, calling dunderiter creates a list iterator object. That is an object of type list iterator. And in actual fact, well, we'll get round to looking at iterators in a minute, but before we do that, let's talk about iterables versus iterators. Basically, we've already pointed out an iterable object like a list doesn't have a dunder next method. It has a dunder iter method, and when you call the dunder iter method, it produces something whose dunder next method can be repeatedly called to produce elements of the sequence. And so basically what that's saying is that when you call an iterable's dunder iter method, you're producing an iterator. So an iterator, which is typically a built-in type created by some call to a factory function, iterators, the most significant thing about them is that they have a dunder next method. But not only do they have a dunder next method, the typical iterator also has a dunder iter method, so that you can actually iterate over it. But the thing that you need to remember is that although you can iterate over an iterator, the results, if you're not careful, will be very confusing. So here we're doing a doubly nested loop, iterating over the test list. And as we would normally expect, we're getting the first element of the first list with the first element of the second list, first with the second, first with the third, then we go to the second with the first, the second with the second with the third, and so on. In other words, we see a complete enumeration of all the possibilities, and that's how we expect iteration to work. And the reason that this works is because whenever we're looping over something in this code, we're first of all calling the iterable's dunder iter method to create a new iterator. So what happens if instead of using an iterable, we use an iterator? And here I'm using a syntactic shortcut that I'll remind you about later on. Basically, you can call something's dunder iter method by applying the iter function to it. That's just the same as if you can call its dunder len method by applying the len function to it. So in this case, I've created two separate iterators, and in the outer loop I iterate over iterator 1, in the inner loop I iterate over iterator 2, and then I produce a result which includes both values. So the first time through the outer loop, we enter the inner loop for the first time, and we see the first value with the first value. Then we go through the inner loop a second time, so we see the first value with the second value. Then the third time, so we see the first value with the third value. So that's the first time through this loop. We've actually used the value Roberta, which is the first value from this iterator here. So then we've terminated this inner iteration. We go back out to the outer iteration, and we get the second value. So now we print outer loop again, but of course at this point iterator 2 has been completely exhausted. And because it's an iterator, when the for loop mechanism calls its dunder iter method, it just produces itself. And so the first call to the next method of that iterator immediately raises a stop iteration error. So the second and third iterations through the outer loop don't actually produce anything, because the iterator in the inner loop was exhausted by the first trip around that loop. So that's what happens if you use two different iterators. It gets even more confusing if you try to use the same iterator in both values of the nested loop, because there we actually extract the first value from iterator 1. We print the fact that we've entered the outer loop, and then of course here we get the second value from that iterator. So the first thing that we see is the first value from the iterator associated with the second value from the iterator. Then we loop round again and call next on that iterator again, so we see the first value with the third value. and then that means it's the end of this iteration, so it goes back out to the outer loop, and of course it's iterating over something that it's just exhausted in the inner loop, and so we don't actually see any more executions of the inner loop at all. And that can be a little confusing if you're not expecting that sort of behavior. So the difference between an iterator and an iterable is that whereas an iterator will have both an iter and a next method, the iterable only has the iter method. So you can see here when we look at test list, it does have a dunder iter, but it doesn't have a dunder next. And when we looked at the iterable itself, then it has both. So there we've just got the code I was demonstrating. This is just to show you that you get an entirely different result. I'm printing out the IDs of the list and of the two separate iterators created by calling the list's dunder iter method. So what I'm trying to underline there is every time you call an object's dunder iter method, you get a new iterator. You don't get the same iterator, because if we had the same iterator, as we've seen, that can lead to big trouble. So that's just the code that I was showing you there, the code I was showing you there, and the code I was showing you there. So what I'm doing here is I'm just creating an iterator from test list, and then I'm showing you that when you call the when you call an iterator's dunder iter method, you just get the same iterator back. And the point of this last value here is just to show that it says false, because the ID of iterator 3 is not the same as the identity of calling iterator 3's ID. They are two different objects. Now, using iterators allow you to adopt some interesting techniques, and one of the things that you can do is you can create an iterator and then you can call its next object inside a loop. And you might think that that's wonderful and marvelous, but again you have to be careful, because here we've got two iterators with different sequence lengths. So the point behind this loop is to try to test both of these iterators. So when I test iterating over IT4, everything works nicely, right? What I'm doing here is in the inner loop, I'm taking pairs by using the for loop mechanism to take the first element and then sneakily moving the iterator along by calling its next mechanism. So with a sequence with an even number of values, that works very nicely. So we get 1 and 2 the first time through the loop, we get 3 and 4 the second time through the loop, and then the for loop tries to call the iterators next again. It sees a stop iteration exception, and so it terminates. Unfortunately, if we use an iterator that's got an odd number of values in its sequence, then what happens is that the first two loop mechanisms, the first two trips around the loop work exactly the same, but then the for loop manages to extract another value from the iterator with its dunder next method. But when we call next here, you can see that the call to next actually raises the stop iteration exception. So that's not terribly helpful. Now, the really important reason for wanting to understand the iteration protocol, oh, by the way, these are just, in the same way that len of object is equivalent to object.dunderlen, in the same way there are functions in Python iter and next which you can use to call those magic methods. So I just thought I'd put that in there with a reminder about the Python 2. So you can write your own iterators if you want. So here, this is the first piece of the code for an iterator that I'm writing, and the idea is that the purpose of this iterator is to produce each character of a given string a given number of times. So the initializer takes a string and an integer argument, which is stored as instance variables, and then it maintains a current position and a current count, which both go to 0. And because it's an iterator, its dunder-iter method is extremely simple. It just returns itself. So we can actually use this thing in a for loop if we want to, by virtue of its idempotent method. But the real magic is in the dunder next method here. So in this case, we're saying, well, okay, if the current position is equal to the length of the string, then we haven't got any more characters, and so we can raise a stop iteration. Otherwise, the result is the character at the current position. However, if after incrementing the count we see that we have returned this character the correct number of times, then we move on to the next character and we set the count back so that we can return the same value for exactly that. We can return the same value, the value of the next string. And I don't think I've actually, yes, there we go. So here's the same code in the IPython notebook. And hopefully, when I've defined that, we will find that if I call that, this basically says this is an iterator which will return each string of the each character of the string ABC 2 times, and lo and behold, it does. We get 2 A's, 2 B's, and 2 C's. And here we're using it in a doubly nested loop, and again with a plus and a times and a plus and an equals and a minus. We get times equals, times equals, times equals, times minus, times minus, times minus. But there, of course, since these are iterators, we see that concern that we were talking about earlier on arising, because iterator 7 has been exhausted by the first location, the first loop across iterator 6. So when we get to the later elements of iterator 6, there's nothing left in iterator 7 to handle those loops. Whoops, did I actually cover that slide? No, I didn't. Okay, so who's used generators and generator functions in Python? Okay, good. The really nice part about generators is that they produce a much easier, give you a much easier way to write your own iterables. So you probably noticed on that last slide, that's a horrible method. There's all kinds of counting arithmetic going on and that kind of stuff. So the nice part about a function with yield in its body is that the interpreter actually recognizes that as a special type of function called a generator function, and when you call it, it doesn't execute the code body, it returns an iterator. And then when you call the iterator, when you call for the next value from the iterator, it's just a next value. So in other words, the yield function here, it doesn't actually yield anything in this particular case, which is rather naughty of me, but basically generators are iterators, and the yield becomes the return value from the dunder next call. So when the generator's dunder next method is called in an iteration, it starts to run the code of the function body, and when it encounters a yield keyword in the function body, the expression that is yielded becomes the value of the next call. So here's a simple generator function, range down, which simply reverses the range and then yields each value. Rather naughty there, I've got a capital I where it should be a small I. Sorry about that typo, hadn't recognized it. Okay, so you can see that if we just iterate over it, lo and behold, we get 3, 2, 1 from a range down of 4. And I believe I've got that there as well. Yep, there's the range down iterator. So I've created my range down iterator. Oh, what happened here? Do I still have... Oh, did I not actually... execute a cell where I didn't define me functions, did I? Sorry about that. One of the nice things about the IPython notebook is you can go back and do things that you should have done earlier. So now I do have an isIterable and an isIterator function. So you can see that the type of generator is a generator. It is not an iterable, but it is an iterator. And you can also see that when I actually call that if I use it in a loop, then I just go down from 4 to 0, which is range 5 reversed. So here I'm just basically using what's called a generator expression. And again, any expression with a 4 inside it is a sequence of the expressions before the 4. So again, I'm not quite sure. Oh yeah, okay, range down itself is a function, but the generator is a generator, and indeed this generator expression is also a generator. And we know from the cells above that generators are iterators. And so having created this expression, we can iterate over it because it's an iterator just like any other generator. Come back. Right. So that's generator expressions. The basic iterable pattern says that you've got to create all your stuff, but the really important thing about an iterator is that it actually has to return, its dunder iter method has to return a new iterator. In other words, the difference between an iterable and an iterator is that an iterable, like a list, uses a factory function as its dunder iter method. So every time you loop over it, you get a new iterator, which is why lists are well behaved in the way that iterators weren't inside nested loops, as we showed in the example above. So we can actually use a generator as our dunder iter method if we want to. So in this case, you can see that this is a method, and so because it contains a yield in its body, methods are functions, and so it is a generator. And you may wonder, okay, I had this I had my iterator up there before, but basically you'll notice that this object here, this class, is a subclass of the standard string. And so you may wonder, why don't I just iterate over self instead of iterating over the str call? And the reason I don't iterate over self is if I iterated over self, that would result in a call to the object's dunder iter method, which would iterate over self, and so you'd effectively get an infinite loop of calls on the dunder iter method. So the nice thing about this object is, because it inherits from string, it does everything that a Python string will do. So in this case, there is the mi string class, and so if I create an mi string, then if I iterate over it, I'm iterating over it using a list comprehension, then we get 3 x's, 3 y's, and 3 z's. Similarly, if we iterate over it in 2 nested loops, you can see that now, because the separate iterators are produced for each iteration over C1 and C2, we still get the correct behavior. We get 0, 0 twice, 0, 1 twice, 0, 0 twice, 0, 1 twice, and so on and so forth. So they are actually well-behaved objects. And again, we can use them just like we can use strings. So if the string here, if we create something here with a value of 0, 1, then it acts like the string 0, 1. We can add them, we can multiply them just like we can, because all the rest of their behavior is being inherited from system strings. So basically here it says the string is iterable. It is not an iterator. If we call it iter, that is not an iterable, but it is an iterator. So calling the dunder-iter method, or the iter function, which is equivalent on an iterator, on an iterable, will give you an iterator. So there's another string class here where we're basically doing the same kind of thing. And you can see that that's just the example I ran above, I seem to remember. Oh yes, but in this case we're using the generator as the method. Okay, well, we're nearly out of time, so that's pretty much all I actually wanted to cover. There were a few things there that we could get into, but it's not really important. Since it's now significantly almost lunchtime, if you have any questions, then ask them now. That's my email address, and just as a reminder, if you'd like to take a look at the slides and the notebooks later on, they are available online. Thank you very much.
So we still have 5 minutes in the official schedule for questions. So sure.
Yes.
Just a quick one. So obviously, the way that we structured uses the next method. How does it work for when the iterables are first of all like a set or a dictionary or something like that?
I'm sorry, how does it work for sets?
Well, basically when it should be unordered, or whether it is in principle an unordered iterable, how is the next method just arbitrary picking an X, or is it?
Well, yeah, basically, although the Python implementation of sets and dicts doesn't guarantee any specific ordering, it does guarantee that if you add the same values in the same order to two sets, you will get the same iteration sequence. So in actual fact, the underlying representation of the set and the dict is based on hash chaining. So there is an implementation that does put the keys in a specific sequence. It's just that the sequence doesn't mean anything to us. So it just uses a linear iteration over the keys. Yeah? Good.
Yes? So the iterator you created, that has an object, right?
I beg your pardon?
That has the iterable that it can iterate over. So can you make changes to that, to the underlying object? Can you make changes to it? Is that?
Oh, what you mean? Can you change an object while it's being iterated over?
Yeah.
Well, you can, but of course the results aren't guaranteed to be predictable. So, for example, here, if we use that class mi string, then basically I'm iterating over the string of myself. So that wouldn't be a particularly good one to modify. I'm just looking for one that we might poke at as we iterate over it. Well, okay, let's just hang on a minute, get to the bottom of the notebook. There we go, right, good. So if I say, for example, class m1 def dunder init self, and we can, in fact we don't even need an init probably, but I'll just put it in there, def dunder iter self. So let's just say, I don't actually looking at it, but yes, the answer is, once you understand the mechanism, then you can understand the results of being able to tweak. Now in Python 3, for example, some of the iterators are what people think that when you iterate over the keys of a dict, it just produces a list of the keys and then iterates over them, but in actual fact the situation there is much more complicated. They use what's called a dict view, and the result is that the dict view will actually complain, it'll raise an exception if you try and change the key set of the dictionary while it's being iterated over.
Yeah, well, I was looking at your iterator, like my iterator,
Yeah.
it has like the constructor or whatever. It has sort of like a self passed as a parameter, so I thought that might be the reason why you could make changes to.
Well, this one here.
Yeah.
So what were you? Yeah, this one actually would be something that we could
S, the
modify if we
second
wanted.
one, yeah, second one is S. I don't know if you pass the object as second parameter S in the init
Okay.
method, then you might be able to make changes to it.
Oh, I see. Right. Okay. So what you're saying is if we say mi equals my iterator, so if we use the list, oh, okay, and better still, say x equals 1, 2, and 3, right? Whoops. Okay, and then my iterator over x, and we'll just use doubling, right? Okay. Whoops, a daisy. All right, so if we establish that, okay, so if I now say mi dot next value from mi, then we should get 1, right? Okay, which we do. So now if I say x dot insert 0 at position 0, don't worry, I'm used to it. I always, yeah. Thank you. There we go. Whoops. I'm not even sure why I got away with that. I must have an object called O, clearly, somewhere. There we go. That's what I meant to do. But anyway, now if we say next of mi again, if we just execute that cell again, then we get 0. So yes, in this particular case, you can tweak around with the underlying iterable that you're iterating over, and it will actually see the changes.
Great, thanks.
Pleasure. Yes.
So, in the typical case where I'm getting sort of access to a database or a cursor or something like that,
Yep.
and I want to produce an iterator object and just iterate through it,
Yep.
the object with the iterable I produce should basically go back to the beginning of that database query every time I create a new generator from it.
Well, yeah, but clearly you have to be careful there.
So what's the intended semantics of the way the iterable works when you've got these streams which are...
Well, I would say that database cursors don't make a particularly good iterable precisely because of the need to store all the values. Effectively, if you're going to do that, then as far as I'm aware, most of the database cursors I know of that you can iterate over, they're actually iterators, or sorry, the results of the cursor execute. They're actually iterators rather than iterables. So in other words, once you've iterated over the cursor, having executed a query, then if you try and iterate over it again, without executing another query, you'll just get an empty result because the iteration will have been exhausted.
So when you wrap it up, basically manage the connection and the query again, so you get new cursors every time you produce a new instance.
You could do that, but whether you'd actually want to or not, you'd have to be alert to the implications, because if you want to effectively, if you wanted to refresh the series of values that were coming out of the database, the only two ways to do that are either to store it when you make the query and retrieve it all, which obviously wouldn't be convenient in the case of a large query, or to repeat the query with each call of dunderita. So there is sometimes a price to be paid, and that's why it's worthwhile understanding the iteration mechanism.
I think that's a nice ending word, so thank you again.
Thanks very much.